Okay, Assalamualaikum and good day. So in this video, we are going to look into the effect of the external capacitance CE to the lower cutoff frequencies. Okay, so we are considering CE only this time. Therefore, C1 and C2 are short circuit. Okay, so this is the overall circuit. So now C2 and C1 is short circuit, so it will be left with CE. So let's look how the circuit will look like now. You can refer to the slide if you want to, but we're going to do this way. Okay, so now this is the circuit. So now C1 and C2 is shorted. So we will have with CE here. Okay, so we can group this R1 and R2 because they're in parallel, and you can call this RB. Okay, alright, so now if you look at this circuit, we have so many branches here, right? When this is not shorted, there's so many branches here. And okay, and then what we do is we are going to consider at the base side only. Okay, we are going to consider look at the base side first. Okay, we only consider once, no need to consider collector sides. Refer slide 40. If you look at the slide number 14, okay, in this green sentence here, if I zoom in, okay, since voltage across base circuit and collector circuit is same with reference to emitter terminal to ground VT1, we will only consider once. This is what it means. Okay, okay, alright, so now we are going to look into this now. Okay, look at the circuit now. Okay, when we are doing to find the Thevenin equivalent circuits, everything here, we are going to short the VS. So when VS is short on the base side, okay, I just look at the base side only. This is your base R pi, and then I just put dot dot. It is there. We're just going to simplify this circuit first. Okay, because remember our target is to find the low cutoff frequency to low cutoff frequency due to CE only. So therefore we are looking for, okay, we are looking for FCE, which is equals to 1 over 2 pi RCE CE. So we are targeting to find the RCE here. Okay, alright, so in order for us to, we have to simplify the circuit here first, and then this, and this one we don't need because we only consider once, because here to the ground and here to the ground is same. Okay, that's what it means. So we only consider once. Okay, now when VS is already shorted, what happened to RS? RS, R1, and this one is R1 parallel to R2. So looking from the base here, okay, what happened is RS is parallel to R1 and R2. Okay, looking from the base. Okay, so I name this as RB equivalent. Okay, I name this as RB equivalent. So RB equivalent equals to RS parallel to R1 parallel to R2. So now it becomes like this. Okay, then we still have R pi here. Alright, to further simplify, I move this R pi towards here. So what it will become? Okay, it will become RBEQ plus R pi. Okay, remember here? So I put it here, so it will become RBEQ plus R pi because they are in series. RBEQ plus R pi. So now I draw again the full circuit. Okay, okay, so now I have this, okay, RC which is parallel to RL, then I have RE and CE. Okay, remember that the current which is flowing at this junction is IB, the current flowing is GMB pi or beta IB, and IE which is equals to IB plus beta IB. Okay, so please take note the current flow. Alright, now in order for us to find the Thevenin's resistance looking from the CE, okay, RCE here, okay, we are going to remove this first. Remove RE and CE first, okay, and replace with a test voltage and test current. Remember, like when you do to find the output resistance in your earlier circuits, Okay, something like this. Can you see that? I remove these two and I will replace with this. Okay? Alright, now. Okay, now. The current flow is IB here. This is with IT and VT. We are looking from this point. Okay, we are looking for the resistance looking from this point. Okay, which we want to call it as RT1. Okay, RT1, which is equals to VT over IT, correct? Okay, because this is like test voltage and test current. To find RT is equals to VT over IT. However, what is IT equals to? IT is opposite directions of IE. Okay, opposite direction. So IT equals to minus IE is also equals to minus 1 plus beta IB. Remember, because IE equals to IB plus beta IB, so it's minus as well. Alright, now remember, before I go further, I want to remind you guys of the Ohm's law. By the definitions, when there is a resistor, okay, and the current flowing through the resistor, and the voltage will have a positive terminal here and negative terminal here, and therefore we equate them, V equals to IR. Okay, now from the base, okay, from the base here, okay, resistance looking at the base is RB total, which I call it RB equivalent plus R pi, correct? Okay, this is the resistance looking at base. Okay, alright, so RB total, okay, is equal to VB, okay, voltage from base to the ground, minus IB, because of the Ohm's law just now. Okay, because if I name VB from here to the ground, okay, so the current must flow there, then we can equate. So VB equals RB total equals to VB over minus IB, correct? And what is VB? VB is equals to VT. Alright? Okay. So we just equate because VB is equals to VT. So VT is equals to minus IB, put it here, times RB total. Can you see that? Why I do this? Because, alright, because we are actually looking for the RTH here. Okay, so RTH, which is equals to VT over IT. So what VT? VT is equals to minus IB RB total. Okay, you see that? VT equals to this equation. And what is IT? Sorry, what is IT? IT is equals to minus 1 plus beta IB. Okay, so therefore, you get, you cancel, okay, you have this. So your IB can be cancelled off. IB cancelled off, minus can cancel off. So it goes to RB equivalent plus R pi over 1 plus beta. Okay, what is RB equivalent? RS plus R1. This is R2, sorry. R1 parallel R2 plus R pi over 1 plus beta. Okay, now we have RT1. Okay, remember that we already removed here just now CE. Okay, actually, okay, this one I didn't prepare, so let me draw again. Okay, so now what we have is we have, let me just leave this camera. Okay, okay, so now looking from the circuit here, okay, now what we have here is we have, let's say this is your base just now. Okay, so we are having one resistance. This is RTH1, because now this is your emitter. We put it together, and then we have CE, RE, and then grounds, and we have, sorry, this is resistor, then we have CE to the grounds. Okay, alright, therefore, okay, so now it is, can you see these two resistors are in parallel? Sorry, cannot see. Okay, can you see now this resistor, these two resistors are in parallel? So therefore I will call this, to be consistent with the one which is in the slides, resistance looking from CE is RTH2. Okay, therefore RTH2 equals to, sorry, cannot see the y, right? R equals to RE parallel to RTH1. We have RTH1 here, so RTH2 equals to RE parallel to, sorry, RS parallel R1 parallel R2 plus R pi over 1 plus beta. Okay, so this is equals to RCE. Okay, all right, so this is your RCE. So you can plug in back to this FCE equation here, okay, and you can find the low cutoff frequency due to the CE only. Okay, now if we have FCE, among FCE, F1 and F2, whichever the highest will be FL, will be the low cutoff frequency. Okay, all right, I think that's the end of this, the end of the our analysis to find the frequency response for the lower cutoff frequency of the common emitter amplifier. Okay, all right, so remember, okay, I hope you can just revise back if you want to. Okay, see you in next video. Bye.